Thank you. So it is a great honor for me to come and speak in this centennial conference for a great mathematician who had a profound influence on many branches of mathematics. Before this distinguished audience, and probably there might be even a few people also in the other rooms, and this spectacular hall, this beautiful city. So the pictures, unlike the other speakers, I did not have the privilege of having close interaction with Erdős, though apparently I've been told that I have met him already as an epsilon. The pictures are from the picture of Erdős is from the Oberwolfach archive of pictures, and people who know Oberwolfach could more or less see exactly which table he's sitting at. So I will talk about self-similar measures, and this is the first half of my talk would be a survey talk. In the second half of my talk, I would describe some recent results, recent in the sense that it's not yet written, that is being written, recent result of mine with better value. So let me start by saying what are self-similar measures. So to begin with, what are the similarity of the planes? So this we all know. It's a composition of a rotation, dilation. In my case, it would be actually a contraction, and a shift, a translation. So this is a similarity. And if I have some finitely many similarities in some probability vector, I can try to find an appropriate stationary measure for the natural averaging operator. That is to say, a measure mu satisfying this condition, that if I take the measure mu and apply to it each one of these similarities and take some average with some weights, I get back what I started with. That's a self-similar measure. And here are some examples, and of course, one thing one should notice is if I have contractions, this measure of mu, there's a unique probability measure mu which satisfies this equation. And here are some examples. So this is a Sierpinski gasket, and it can be obtained by, it's a self-similar set for the three similarity maps. Or if you like, the natural uniform measure on the Sierpinski gasket would be the self-similar measure for these three contractions with equal weights, where these vectors form the vertices of an equilateral triangle. And of course, there's nothing, you could do this in any dimension, 3, 4, 5, 1. These are self-similar measures. And when there is no overlap between, or minor overlaps between, you take a set and its images under these similarities, and everything is quite easy to analyze. For example, easiest case would be the Cantor set, where everything, even so in the Sierpinski gasket for the particular set of three contractions that I've described, there is some overlap, but it's a minor overlap, and there's sort of various ways to formulate what a minor overlap is. The most popular seems to be the open set condition, which means that there's an open bounded open set, so that each one of these contractions map my open set into itself, and the images are disjoint. Now, this open set is not uniquely defined, but one possible choice is the interior of the green triangle in this picture. So such cases, you could understand everything. You understand the behavior of the measures, or somehow, in many respects, once you have such a condition, you understand the self-similar measure. For instance, you understand the dimension of the measure. If you have an open set conditions, then there's a simple formula to calculate the dimension of the measure. Now, dimension of the measure, I should say dimension of a set, that's somehow a canonical thing. You basically take maybe Hausdorff dimension, or you can talk about some other notions of dimension. Dimension of a measure, you need to say something. So for me, dimension is pointwise dimension. It's dimension as determined by the volume of small balls. And in the cases I would look at, this ratio, this limit would exist almost everywhere and be constant almost everywhere. So there's a nice formula, easy formula for if my contraction satisfies the open set condition for the dimension of the measure. It's very easy to show. Now, if you look at this formula, you would notice that the dimension blows up as the contraction ratios, lambda I, go to 1. If you contract less and less, then this formula gives you dimension which is bigger and bigger. And obviously, if you have a measure on RD of dimension bigger than D, you know you are in trouble. So this formula must fail if there's no condition on the set. And okay, this proposition in this form is due to Moldin and Simon. It's actually related to perhaps the first result on self-similar measures, which discuss in a minute. But basically, if you have a self-similar measure, it has a choice. So either it's completely singular with respect to the Lebesgue measure, or it's basically the Lebesgue measure restricted to its support, restricted to the self-similar sets corresponding to the same collection of contractions. In particular, a self-similar measure may either be singular with respect to the Lebesgue measure or absolutely continuous with respect to the Lebesgue measure. And this is actually an easy statement to prove, so maybe I would prove it. So suppose I have some n contraction similarities and some weights. So as I said, there's a unique probability measure satisfying this stationarity equation. And any probability measure, any measure, I can decompose into sum of the continuous part and the singular part. Now, by uniqueness of this composition, you see that the singular part and the continuous part, each one individually has to satisfy this equation marked by star on the slide. But I said that means there's only a unique measure, so the only way this could happen is if I can't normalize the continuous and singular parts to be probability measures. That is to say that either the continuous part or the singular part is a zero measure. Okay, so that's very easy. A measure which is self-similar can either be continuous or purely singular, nothing in between. So perhaps the simplest possible self-similar measure are what's called Bernoulli convolution. And it is here that we would connect with some early work of Erdős, which remains very much fresh and influential to this day. Now, I say it's the simplest possible because it's just a one-dimensional example, two contractions, nothing can be simpler, but of course, as it turned out, it is not simple at all. It's actually quite very hard to analyze. It's extremely hard to analyze. So I gave here the two similarity maps on the line for which I look at the corresponding self-similar measure. A way which to me is more intuitive to think about these measures is that I take the random sum of this series, summation from 0 to infinity of epsilon I, lambda to the I, where each epsilon I is an unbiased IID plus or minus one random variable. Okay, so this random sum, of course, converges, and it gives me a point sampled according to some probability distribution. This is precisely this Bernoulli convolution nu lambda. And if the contraction ratio is more drastic than a factor of 2, then everything is fine. This is an open set condition, in fact, is satisfied. The support is totally disconnected. The dimension is exactly 1 over the logarithm to the base 2 of my contraction. Everything is completely understood. Once I go beyond 1/2, then there's an overlap. It's easy to understand what would be the corresponding self-similar set, the set which supports the self-similar measure. This would just be an interval, a specific interval that I wrote here on the slide. But what the measure is actually an extremely, extremely tricky question. But of course, at least we know that either it's equivalent to Lebesgue measure on the interval, or it's singular with respect to Lebesgue measure. So the Bernoulli convolutions were introduced by Jessen and Wintner in 1935. Some easy observations is that when a parameter is exactly 1/2, then if I take a sum of plus or minus 1/2 to the I by expansion base 2, by binary expansion, I get uniform measure on the interval -2, 2. So that's easy. And another easy observation is that if I have a parameter lambda, in the Bernoulli convolution parameter lambda is absolutely continuous with respect to Lebesgue measure. Now if I take nth root of this parameter, then it's a convolution of rescaled images of new lambda. So if the new lambda is absolutely continuous, new lambda 1 over n is absolutely continuous. What this implies is if I look at the set of parameters for which the Bernoulli convolution is absolutely continuous with respect to Lebesgue measure, this would be a subset of the interval between 1/2 and 1. And it certainly contains 1/2. And 1 is the limit point of this set. Okay, so these are easy observations. And essentially, a big question, maybe the big question is to understand which parameters, what can be said about the set of parameters for which the Bernoulli convolution is absolutely continuous. And Erdős has 2 deep results which he proved, I think, in his 20s, some 75 years ago, so approximately. And the first thing is that certainly this question is not a trivial question. I mean, there are parameters for which the Bernoulli convolution is singular. And indeed, if you take the corresponding self-similar measure, you take its Fourier transform, then it would not, the Fourier transform will not decay, which by the Riemann-Lebesgue lemma implies that the measure cannot be absolutely continuous with respect to Lebesgue measure. And this happens if, excuse me, if the inverse of lambda is a Pisot number. Now, what is a Pisot number? A Pisot number is an algebraic integer, which is a real number, bigger than 1, and all of its conjugates, whether real or complex, all of its Galois conjugates have absolute value less than 1. This is a Pisot number. The most famous Pisot number is a golden mean, 1 plus square root of 5 over 2. Its only conjugate under the Galois action is 1 over the square mean. But it's not the smallest Pisot number. The smallest Pisot number is known. It's this particular number that I've written, the root of x cubed minus x minus 1. It's an isolated, there's no Pisot numbers near it. The next Pisot number is sort of bigger. I don't remember what it is, but it's a bit bigger. But there's infinitely many Pisot numbers in the interval, relevant interval for us between 1 and 2. And the first accumulation point is exactly the golden mean. And I guess an obvious question, which is quite wide open, is perhaps the only parameters lambda in the relevant interval for which the Bernoulli convolution is not absolutely continuous are just those found by Erdős. Perhaps there is no more. In particular, if you take 1 over the smallest Pisot number, you get some number which is a bit above 3/4. So a special case is maybe inside this interval, there's no parameter for which the Bernoulli convolution is singular with respect to Lebesgue measure. One could be a bit more modest and ask, does there exist a lambda naught strictly less than 1, so that for every parameter lambda between lambda naught and 1, the corresponding Bernoulli convolution is absolutely continuous with respect to Lebesgue measure? And if I understand correctly, at least initially, Erdős believed that the answer is no. Though probably if one asks the experts today, the general belief is that the answer is yes. So Erdős in 1940 proved another sort of deep result about these Bernoulli convolutions, which was later Professor HUN, who introduced me, noticed that the argument actually gives more than what was advertised. So in fact, the theorem of Erdős and HUN says that for any epsilon and n, there's some lambda 1 very close to 1. I don't know that every parameter bigger than lambda 1, the Bernoulli convolution is continuous, but but in fact, outside a set of exceptions of very small house of dimension, not only is the Bernoulli convolution absolutely continuous, but in fact, the Fourier transform decays as rapidly as you wish. And as you would see, I mean, this result is actually has been found some very nice use, or at least techniques, very recently. Now, in 95, important progress in this question, and I'm talking about Bernoulli convolution. It's somehow a very simple example, but in fact, while talking about Bernoulli convolutions, in fact, we're sort of studying a larger class of problems which have connections to many areas of mathematics, but okay, I'm sort of fix my attention on the particular to avoid saying generalities. So Solomiak proved in 95 that for almost every parameter, inside the relevant range, the Bernoulli convolution is absolutely continuous. In fact, it has an L2 derivative. And this was strengthened in a very nice work by Perez and Schlag, which unfortunately I don't have time to describe. Very, very recently, there's been, really in the last year or so, there has been a fairly dramatic breakthrough. So sort of one instance of which is the following theorem of Hochmann, which basically says that outside a set of, which is in some sense explicit, don't press me to say in what sense explicit, but aside a somewhat explicit set of parameters of house of dimension 0, well, maybe the Bernoulli convolution is not absolutely continuous, but the dimension is 1. So what explicit means is hard for me to define, but at least it means that there are many numbers, actual numbers for which we know that the Bernoulli convolution is of dimension 1. In particular, all rational numbers in the interval, the Bernoulli convolution would have dimension 1. And this was strengthened by Shmerkin. I've corrected one misspelling. Shmerkin does not have a C. It's misspelled his name, but not a theorem. The set of parameters for which a Bernoulli convolution inside the relevant interval, for which a Bernoulli convolution is not absolutely continuous with respect to the Lebesgue measure, has 0 house of dimension, which is a very strong result. And it's proved by combining Hochmann's result with the Erdős-Kahn argument. Using the observation, so Bernoulli convolutions you could easily present as a convolution of two measures. Maybe you take all those, one in every million digit you sort of take out and put it separately, and then you present the Bernoulli convolution as a convolution of two measures, one of which, by the Hochman argument, you show is of dimension 1. The other, by the Erdős-Kahn argument, you show that it's out of a set of very small house of dimension has some polynomial decay of its Fourier transform. And if you take two measures, one of dimension 1 and one with any kind of polynomial decay of the Fourier transform, you convolve them, you get a measure which is absolutely continuous with respect to the Lebesgue measure. Now, I wanted to present another, maybe even more striking instance of this general theorem of Hochman. So here's another what's called iterated function system, three similarities. So I take 1/3 x, 1/3 x plus 1/3, and 1/3 x plus t over 3. So these are three contractions by radius 3. If you take the naive entropy formula, which is always an upper bound, naive dimension formula, which is always an upper bound of the dimension. The dimension, naive somehow calculation gives you dimension 1. And what Mike Hochman shows is that for every parameter except the rational numbers, for which there's actually an analysis by Kenyon, for every parameter which is irrational, the dimension is of the self-similar measure is 1. And maybe an indication that this is not a trivial result, even though, I mean, the naive dimension formula works despite the fact that there are complicated overlaps. This measure is certainly not going to be, in this case, absolutely continuous with respect to the Lebesgue measure. This follows, essentially this measure mu t is a projection of the uniform measure on the Sierpinski gasket I've shown before on a line. And it's a general theorem of Bezikovich that when you take a measure of dimension 1, so honest dimension 1 on the plane, which is not rectifiable, then in almost every direction the projection would be singular with respect to the Lebesgue measure. And in this particular case, Kenyon actually showed that the projection that these mu t's are singular with respect to the Lebesgue measure for every irrational parameter. So this is sort of quite satisfying. In one of these few cases, we actually know something. That as a community, we actually know something. So this maybe concludes the survey part of the talk, and now I'd like to describe some work that I've been doing with better value. And indeed, I mean, this work is continues work that better value has done previously on his own. And the starting point is a remarkable fact. It's a truly remarkable fact, which was somehow implicitly, I think, hidden in Professor Moldin's talk yesterday. So in this talk about Steinhaus sets, there was a dramatic difference between dimension 2 and dimension 3. And somehow the biggest difference, at least in these kind of questions between dimension 2 and dimension 3, is a completely counterintuitive fact that you could find finite sets of rotation, so that when you take any L2 function, no regularity, no nothing, any L2 function, which is orthogonal to the constants, and you average it with respect to these finitely many rotations, you would decrease the norm. This is a sort of very strong and counterintuitive fact, and just the existence of such a set of rotations is already enough to, as was discovered by Rosenblatt, enough to resolve the Rusevich conjecture, which was regarding invariant means on the sphere. Using this observation, Margulis and Sullivan and Drinfeld were able to resolve the Rusevich conjecture. And I mean, this is not somehow, here's a very concrete example, the most concrete one could possibly want. So you take the three axes, the x, y, and z axis, and you rotate around each axis by arc cosine of minus 3/5. Then this contracts the L2 norm of any function of mean 0 by this ratio of square root of 5 over 3. This is a deep, this precise value is actually quite deep. It uses proof of the lean of the classical Ramanujan conjecture. But if you are willing to settle for any kind of spectral gap, then in fact it's much more prevalent and you don't need to rely on such very delicate arithmetic facts. There's a general theorem by Bourgain and Gambard that if I have a set of rotations which generate a dense subgroup of SO3, and all of the coefficients of these theta 1 and theta n considered as a 3 by 3 matrix, all of the coefficients are algebraic numbers, then the corresponding averaging operator has spectral gap both on the sphere and on SO3. And one implication, I mean, there's a close connection between this type of spectral gap and equidistribution. So one implication of this is if I sort of randomly choose one of these 2n rotations each time, subfull same point, and do this after k steps, I get some exponential number of points which are equidistributed in an exponentially small scale on the sphere. Okay, so this is a very close connection between this type of spectral gap and the speed of equidistribution of a random walk. Now, so sort of one thing that Vario and I proved is that if we have a subset of SOD, so that the corresponding averaging operator has a spectral gap, then in fact what we couldn't prove for the Bernoulli convolutions is correct. There's a small interval, so there's if I take I construct similarities, similarity maps using these rotations, and if there's, okay, things are not degenerate, if there's no common fixed point to all of these contractions, then for big enough lambda, some small interval around 1, the corresponding self-similar measure is absolutely continuous with respect to the Lebesgue measure, actually has Fourier coefficient which decays by as fast as an arbitrary polynomial, which in particular implies that the Radon-Nikodym derivative is the differentiable of any order. Now, okay, this is sort of, I wrote a theorem where you could put various bells and whistles, you could give different weights, you could, using a result of Miklos-Abert, you could use different contraction ratio. As I mentioned, this gives a positive answer to an analog of the Bernoulli convolution question. So sometimes, it often happens in mathematics that the hardest questions are perhaps the simplest ones to state. In these cases, we understand self-similar measures better. And you can even vary the contractions you do at every step. Everything is very uniform in all possible parameters. Now, the theorem is a corollary of a result about spectral gaps, which is in fact perhaps the main theorem. It's stronger. These estimates on self-similar measures are, in fact, they don't use the full power of this spectral gap result. So let me explain that. So if you take the group of isometries of RD, which is just a semi-direct product of SOD and RD. It, of course, acts on L2 of RD. It acts unitarily on this space. And the space of L2 functions, there's a very natural isometry. It's equivalent to the Fourier transform gives a unitary map between L2 of RD and itself. So through the Fourier transform, I get a very nice action of the group of isometries on the Fourier space. And this action, what you do is you take, so translations in physical space correspond to multiplication by phase on the Fourier side. So what I do is we take a function, you rotate it by the rotation part of my isometry, and then you apply a phase which corresponds to the translation part. Now, you see that once you present the action in this way, that the action of the isometry group on L2RD is certainly very far from being irreducible, because on every sphere of radius r, it remains, you sort of, the whole representation decomposes into an integral of representations on sphere of radius r. And on the sphere of radius r, we have this particular. So now we have a representation on the sphere, on a d-1 dimensional sphere, which you get by taking the representation, the usual representation, regular representation of, appropriate representation of SOD on the sphere and twisting it by this character. So I have here a one-parameter family of representations. And if I have some collection of isometries, I can look at the averaging operator and see how it acts on each one of these representations. And so the main theorem that Vario and I show is that if we have, let's say a symmetric sort of minor issue subset of the isometry group, so that the rotation part has a spectral gap. By applying it enough times, you could just as well assume that the rotation part has gap at least 1/2. If it's not anything less than 1 would work, but then I would have to add another parameter to the theorem, and it would be harder to explain. And you assume that every point is moved by at least some amount by at least one of my isometries. That's basically what 2 and 3 amount to. Then you have a norm bound on the averaging operator, which is uniform outside of r close to 0. When r is equal to 0, this is just the averaging operator on the sphere. It has a spectral gap, but there is the constant function which has eigenvalue 1. So near this r equals 0, you obviously would have, there would not be a decay. So this is more or less the best one could hope for. And this is perhaps a slightly technical statement, but it has, as one corollary, this fact about self-similar measures, and there would be another implication about random walks, which I would present at the end of my lecture in a few minutes. Kohns and Guvarch have a similar spectral gap result, but the result is not uniform in the parameter R. In fact, for many applications, this uniformity is crucial. Indeed, it's people who work with spectral gaps, I think, have probably noticed that the power of spectral gaps comes when the spectral gap is uniform in a family. So what's the connection between the somewhat technical statement on spectral gaps and self-similar measures? So suppose I have some kind of similarities, and I have, which are constructed from translation and rotation, and I have a self-similar measure. And the fact that the measure is self-similar, it satisfies some kind of stationarity equation, implies some equation about the Fourier coefficients of the measure. And okay, you can write down what this stationarity equation implies about the Fourier transform, and what you see is that after you massage it a bit, or not too much, it gives the following statement. So if I take psi of r would be the Fourier transform of my self-similar measure restricted to a sphere of radius r. And I rescale things so that now all of my psi of r's are functions on the unit sphere. Then psi of r, so the Fourier transform at radius r, is given by the Fourier transform at a smaller radius, at the radius lambda r, when I apply to it this twisted averaging operator. So if you have this, now, okay, some observations about these Fourier transforms on spheres. Well, certainly the Fourier transform probability measure is always at most 1. That's not saying much. And certainly these self-similar measures are compactly supported, and you can estimate the size of the support, etc. So there's an easy bound on the L infinity norm of the gradient of my of the Fourier transform. So there's a bound which becomes worse with the r, but there's some bound on the gradient of my functions restricted to a sphere. I rescaled everything, so so this bound becomes weaker as r goes to infinity, but doesn't matter too much. Now, if I had some kind of bound on the L2 norm of these operators, then if r is my radius at Fourier space is somewhere between lambda to the is roughly lambda to the minus n, I apply this procedure n times, and I see that my L2 norm is bounded by the L2 norm at the smaller radius, which is at most L infinity norm, which is 1, times an exponential in n, a small exponential in n, which means that it's that I have a polynomial decay of the L2 norm, and because I have some control over the derivative, the L2 norm implies something about L infinity norm. And as lambda becomes smaller and smaller, you get better and better estimates. And in fact, the same procedure gives something which is, okay, maybe also of interest, that if you take the Fourier transform of such a self-similar measure for any parameter, it has some polynomial decay. And I will end probably a bit before time, but maybe if there are 7 more lectures to go today, it might not be a disaster. I will end with another corollary, which does use the full force of the spectral gap estimates. It sort of should be equivalent. About random walks, which is another subject on which Erdős had left his mark. But this is not the usual random walk. So I take n isometries of RD, so that the rotation part has a spectral gap, and I don't want it to fix one point. And now I take a point in RD and apply to it randomly one of these isometries. So after L steps, I get some kind of distribution. It's quite easy to see that the variance is like the usual random walk. After L steps, the variance is L, the standard deviation is proportional to square root of L. And okay, you expect random walk to behave like a Gaussian, so it does behave like a Gaussian in the following very strong sense. So you take this random walk and you see what's the probability that it would belong to a small ball around some point P. Well, it's the same as the probability that a standard Gaussian shifted and rescaled by square root of L times some constant standard deviation would be in the same ball, plus an error term. The first error term, as long as the point P is somewhere near where this Gaussian lives, the first error term is basically 1 over L, the probability of that this Gaussian would be in a small ball. So that's sort of the first error term. Which is always smaller than the main term by a factor of L. The second error term is something which doesn't allow you to take R to be very small, but it allows you to take R to be as small as exponential in L. So you have here that this random walk is distributed like a Gaussian on a scale which is exponentially small in L, which is certainly something that does not happen for the regular random walk on R3. Okay, so maybe I'll end with 2 questions. You cannot end a lecture on, maybe before I go to the questions, there were some notes. Some of them I said, but one important thing I didn't say is that our result on random walk is basically we plug the spectral gap estimate in the previous work of Vario. Now this work of Vario is quite beautiful. It's very general. It doesn't need any spectral gap assumption. It's not as sharp. I mean, it's still quite sharp. It gives you that this random walk is equidistributed for a scale which is as small as e to the minus 4th root of L, which is already quite strong. Okay, so now I'm not don't have the infinite supply of deep problems that Erdos has, but maybe a few problems might be relevant. So the first one, not very original, but it is a deep question, and it is a question which I think is worth thinking about. So I made quite a bit of fuss from something which I think one should make quite a bit of fuss of, this spectral gap of finite groups of rotation on L2 of the sphere or L2 of SOD. Now, is it true? I mean, I mentioned the result of Bourgain and Gambourg, but perhaps this assumption that was not quite natural, that the entries of the matrices of these rotations are algebraic, can be removed. Perhaps it is true that whenever I have a symmetric finite collection of rotations which generated then subgroup of SOD, the corresponding averaging operator has a spectral gap. To the best that we know, this could well be true, maybe even likely true. And the most embarrassing thing is that even though we know that this is true under some condition which is not too frightening, that the coefficients are algebraic, even if you take a random collection of d rotations, it is not known whether the corresponding averaging operator has a spectral gap or not. Quite embarrassing gap in our knowledge. And another remark, so in the case of Bernoulli convolutions, the problem is complicated in part because the truth is complicated. So when you look at the parameters where somehow the naive dimension should be 1, where naively you would expect the measure to be, the self-similar measure to be absolutely continuous, well, Erdős has shown the situation is quite complicated. There are parameters for which the convolution is absolutely continuous. There are parameters where it is certainly not absolutely continuous. But for this case that Varya and I have studied, that the rotation parts have a spectral gap, there seems to be no reason to expect there to be any parameters, any counter examples. One would expect, or at least I would expect, that whenever the parameter is sufficiently, this contraction is sufficiently large that there's no obvious reason why the measure has to be singular with respect to the Lebesgue measure, it has to have dimension less than the space of the dimension of the ambient space, the corresponding self-similar measure should be absolutely continuous. Okay, thank you. I don't know. I'm not sure. I mean, it's actually probably the answer is yes. I think there's a paper of David Fisher which does something like that. I'm not sure, but I think there's a paper of David Fisher which does it.